Croptastic, the podcast by InnerPlant. We're starting off this season with a very special episode coming to you from here, Croptastic on Stage, our live event taking place at the Georgia Aquarium in Atlanta. So Shelly, tell me about Croptastic on Stage.
Croptastic on Stage is our conference, and we do this now. This is our second one. The first one was in Iowa, and now in this beautiful venue in Atlanta. It's the place for us to get our partners and, most importantly, our customers, our farmers together and talk about the work that we're doing, the progress in the last year, and then just continue to build that relationship as we go forward.
What can guests look forward to in terms of programming?
The different progress over the last year, the perspectives about the future farm, what is that going to look like, how are things progressing towards that, and then just as we continue, now that we're commercializing our Crop Voice product, we're going to bring use cases from the farm and understanding of what you can do with early detection of fungal pressure and just a better way to farm manage your field. This year, based on feedback from last year, we heard that really what people want to see is more of our science, and we decided to devote a whole section and bring a science fair into Croptastic on Stage, and we have an area where scientists have flown in to show the different things that we're doing in the lab and the opportunity to work on actually transforming some plants or seeing the detection mechanisms that we use and seeing the progress that we've made on the science front.
These plants have been engineered to produce the green fluorescent protein that we use as a signal for fungal disease in the field, and these are normal plants that haven't been engineered. And so the fluorescent protein, the way they work, they absorb blue light and emit in green wavelengths. So this blue laser excites that green fluorescent protein, and emits green. And in this case, it doesn't, but they both look blue because you're seeing primarily reflected light. So the protein is also activated by the sun or really any light. Now, if we block that reflected light with these blue blocker sunglasses, then when we look at the engineered plants, you'll see they look green.
Oh, wow. Yeah.
And these look red. Now, the red is chlorophyll, which is natural to all plants. In this case, we've engineered this green signal. So if you're a tractor or a drone and you're going across different plants, it's very easy to tell the difference between a non-infected, non-diseased plant, a healthy plant, and a diseased plant. And so that's how we are able to plant these in fields and in sentinel plots and tell exactly when the plants are infected, and farmers know when to treat.
Hi, my name is Ashley. I'm part of the tissue culture team at InnerPlant. Well, today I'm going to show you the overview of the tissue culture process. To start off, first and foremost, we're going to prepare our tissue and bacteria. So tissue culture is a sterile process, so it's very important that we start off with a sterile tissue. So we're going to be using chlorine gas to sterilize the seeds. Then additionally, we're going to be growing up our agrobacteria for transformation. Next, we're going to be collecting the embryos. So our tissue is embryos, and we're essentially, in order to do this, we're going to be removing the seed coat and picking out this little tiny piece here. After that, those embryos go into the agrobacteria solution. So we're going to be resuspending the agro and putting it into solution, letting it hang out in there for about 40 minutes. During that time, we're going to be sonicating them, which is creating small wounds in the plant cell. So in the wounds, the agrobacteria can better inject our DNA. After the incubation time, after the inoculation, they're going to go on co-cultivation media, which is essentially just a neutral media where the agrobacteria can really use its machinery to put our plasmid into the plant cell. So the molecular team has created this plasmid that has our protein and also a selectable marker on this DNA. So the selectable marker is important because it allows us to select our transgenic plants. So as we use spectinomycin and glyphosate as selectable markers, the spectinomycin causes leaf bleaching. So the bleached leaves have no chlorophyll, and so the ones that are green and healthy are transformed. With the glyphosate, we kind of call them spikies. So the glyphosate doesn't allow the plants to elongate or create a broad leaf. So the plants with the broad leaves and the elongation are the ones that are transformed. So the transformed plants are then selected and then transplanted into our growth chambers on site. They kind of start off in this high humidity environment, and so we need a period of acclimatization to get them prepared for the greenhouse environment. So once they get to a certain size, we'll transplant them out to the greenhouse where the seeds are harvested and then collected and planted out. That's taken to the phenotyping team where they'll be sprayed with fungus and then assayed from there. Additionally, we've recently started working with corn. So the corn transformation process is pretty similar. So we are using the embryo as a tissue, except each one of these kernels has its own embryo, and they're tiny. So we'll do the same process using the agrobacteria, putting them on the plates. And after that, the main difference between the corn transformation and the soybean transformation is that the corn transformation is an indirect organogenesis. So there's an intermediate callus phase that the shoots and the roots will grow from.
So this is the field equipment for our Crop Voice product, which actually sits in the field and takes fluorescence and RGB images of the plants daily and uploads it using a cell modem in there. Inside this sun shield, there is a transparent plastic tube in which there are 2 cameras, a control board, and lights for excitation, as well as white LEDs for the color image. And on the table, there are 5 plants, and only 3 of them are fluorescent. So when I turn on the excitation blue light over here from the computer, you can see the 3 of them light up on this screen and 2 of them don't. So the 2 of them are wild types, and then the 3 are fluorescent plants that are designed to flourish all the time. And in the field where the sensors respond to the fungal stress, they will light up similarly, and we can use the image intensity values to detect when they have responded to the fungal stress.
My name is Brandon Rasmussen. My background is actually in planetary science. I'm not an agronomist. My graduate degree was looking at hyperspectral imagery on Mars and looking at billions of years old rocks. And after that, I spent a couple of years working at Planet on a hyperspectral satellite mission, which is now operational and delivering data. But here at InnerPlant, I'm the satellite guy. And ultimately, my job is to find out how we deliver large-scale insights to farmers in the future. So my job is to dream big. Shelley, brought those dreams down a little bit today, talking about how we have to really focus on this cool commercial product that we have now. But my job, being the only satellite guy at Planet, is to think about the far future, which is a pretty cool spot to be. So ultimately where we are today is we've proven out multiple different types of detection, and in the future satellite is going to, we envision, being the primary way, just because it's so scalable, so cheap compared to all the other options. But there's places where satellite won't work well that we're going to want drone availability. The proximal detection, which you can see over here from Push, will always serve its purpose as well. And our partnership with Deere to become a part of See and Spray will serve as a completely different need. So I'm going to talk about satellites, but ultimately it's going to be an ecosystem of how we detect this. And in that end game, where we're on millions of acres, we're in good germplasm, we have other good traits stacked with. Our only goal is to image crop stress globally and to deliver low-cost insights for farmers. Best way to do that is with satellites, but as I said, satellites don't work best in some locations. So our first chance at actually doing satellite detection was January of last year in Argentina. In this case, you're looking at a 10-acre field, and it's full of those plants right there. We call them always-on calibrator plants. So gene is tied to a metabolic gene where it's always on, always producing the protein. So it doesn't have to be experiencing fungus, and it's glowing. The cool part about this is essentially, looking at the big 11 by 11 kilometer area and seeing how our field stands out. This is basically values of estimated fluorescence with the color palette. And then zooming in closely, you can see our little 10-acre field, and none of the retrieval around it is above background. So it was our first chance. We finally had enough plants to do this. We succeeded, but did we get lucky? That was the next question. And we replicated the results in North Dakota during the summer of 2024, the northern summer, and replicated the results basically with same target design, but different growing conditions, different atmospheric conditions, same satellite, same signal. But ultimately, we wanted to do a lot more than that this past summer. And we had two other really major experiments trying to figure out kind of what the limits of satellite detection could look like in the future. So what we have here is basically we took those calibrator plants and we mixed them with different levels of a commercial variety to simulate lower levels of fluorescence, so less signal, harder to see from the satellite. And in this case, you're looking at a 1-to-3 ratio, 50% ratio, etc. And this was essentially the result. It was pretty great to see that at the 50% or so level, so 50% commercial plant, 50% fluorescent plant, we were confidently able to detect it in many different images. Much harder at the 25%, so we're starting to feed back to the biology team of how bright we need our plants in order to detect with current hyperspectral satellites. And similarly, we're interested in what's the smallest target that we can see. So both of those things are kind of confounded and work together. But here we have kind of a third replication of the Argentina experiment with 10 acres of pure calibrator plant. Then we have a 50% mix, which is a replication of the Iowa experiment that I just showed a minute ago. And then we have all of these different targets, which are sized specifically to be detected by these hyperspectral satellites. So 60 meter, 45 meter, 30 meter. And then looking at the fluorescent image was the results basically exactly as we expected them from the Iowa experiment, which is that even down to a single pixel, we're able to see it, but it starts to become hard. And then when we get down to the sub-pixel level, which is these 15-meter targets down there, which would be 4 pixels in a single pixel, 15 meter, 15 meter, 15 meter, 15 meter, it's almost undetectable. And you can see the level here in the 50-50 mix is significantly lower than the calibrator plants. That's good. That's how we want it to behave. So I was there taking a bunch of drone images all throughout the summer and validating the satellite results with on-the-ground spectrometer and drone data. So if you squinted really, really hard, you'd be able to see little targets over here in the corner of the field. And those are the drone targets. So this is a half-acre little target that we imaged mostly from higher altitudes of about 120 meters, which is the highest that you can fly drones. And even from that really, really high measurement, we're able to make out targets significantly smaller than a meter squared, which is a pretty small group of plants. And ultimately, our target resolution that we're kind of working with right now, but is really up in the air depending on lots of feedback from farmers and further field trials, is about a 1/4 acre. Like if we're able to detect a 1/4 acre from space, we're happy, and that's about where we are with the hyperspectral satellites.
A big thank you to all of our partners, customers, and of course our InnerCircle members who joined us for our Croptastic on Stage conference in Atlanta, Georgia. And thank you for joining us for this very special kickoff of the Croptastic Podcast 5th season. As always, please feel free to share any comments or feedback you have with us on our LinkedIn page or via Twitter at @inner_plant.